In this lesson, we're going to examine the idea of rate of change again. We're going to try and get away from a graphical model and develop more of an algebraic model, one that will give us the exact same answer every single time. In particular, we're going to use this when we do IROC, so instantaneous rate of change. So the graphical method was okay, but each of us had to use our own eye to decide where to draw that line. And because of that, we probably all had slight differences in where we drew the line, and we had slight differences in our estimations, which then changed the actual calculation of slope. We kind of want to avoid that. If we have differences, well then how exact is our actual answer? So today's idea is we're going to develop a function for gradient, or in other words, slope. We know slope is the instantaneous rate of change at a certain point. So if I can have a model or a function, an equation, well, if we have the same equation, we're always going to get the same answer, right? So we can develop something similar every single person. So what are we going to start with? We're going to try and figure out a function at a certain point, any given point. And once you plug that point in, we can find out the IROC. We really call this the derivative. Okay, so if you come across the word derivative, that means the gradient function. And the process of finding it is known as differentiation. And we call that taking the derivative. There are some different notations for derivatives. So f prime at x, or y prime, or dy dx. What that means is the derivative of y in terms of x. How y is changing as x changes. If you think about that, that really means our y's over our x's, or in other words, slope. Slope, gradient. Gradient, derivative. There's a bunch of different words here that we have to kind of get familiar with. So let's take a look at how we can do this. So I have a graph here, a bunch of graphs actually, and all the graphs of a parabola, a really standard parabola. And the tangents have been drawn in for us at a variety of points, at -3, -2, -1, 0, 1, and 2. And I want to use the triangles in the diagrams to figure out the slopes. In other words, the IROC, the instantaneous rate of change at each of those points. So if we take a look at the first graph, here's where x is 3. This line that we drew right here, you can see the line, is the tangent at x equals 3. So in other words, it's finding the instantaneous rate of change at that point. The slope. Let's say we can use the shaded triangle. So we look at the slope, it goes down 1, 2, 3, 4, 5, 6, and over 1. So the slope, we'll call it m, is -6 over 1, or in other words, -6. The next graph shows the exact same graph, the same function, still y equals x squared, but our tangent's now at -2. The slope of this tangent is down 1, 2, 3, 4, and over 1. So our slope is -4 and over 1, or just -4. The next graph is at -1 right here, and its slope is down 2 and over 1, or in other words, -2. Okay, if we go to the next set of graphs, the graph at 0, that would be this one right here, where our slope is this nice horizontal line here. In other words, the slope is 0 over 1, or just 0. And tangent at 1, our slope is up 2 and over 1 this time. So up 2 and over 1. And the next one, or the last one, at 2, our slope went up 4 and over 1. In other words, just 4. And the last idea over here is what happens at 10. Now, I don't have that graph anymore, but there's a pattern. Hopefully you can take a look at the x coordinates themselves. So that's these numbers. And the slopes. If you take a look at those, you might notice that there happens to be a pattern. Every single number appears to double. Okay, positives double, the negatives double, even 0 doubles. So based on that, what should be the slope at 10? Our slope should be 20. Okay. So a pattern is great, but we want to turn that pattern into a formula. So if you actually stop and think about it for just a second, you might figure out that the derivative function, that would be an equation based on the graph that we were using, is actually 2x. In other words, it's double times 2, whatever x value you happen to have. Okay, so our objective is to take an equation like this, a function, and turn it into a derivative. And there's a pattern there. Okay, notice that our exponent's a 2, and we have a 2 up front. And also that we had an x squared, and now it's just an x to the 1. We can extend that idea, and there's actually a huge development to this. We're not going to worry about it for our purposes. We're just going to tell you what the formula is, that for any polynomial, that means any x to the power of something, okay, if you're given an equation in that form, its derivative is always take your exponent, put it down in front, that's why it's the letter n, times x to the n minus 1. Subtract 1 from your exponent. It works for every single polynomial. So, for example, if I have y equals x8, its derivative, so y prime, will be 8 times x to the 7. My exponent came down in front, and I subtract 1 to get the new exponent. And if I had y equals x5, y prime would be 5x4. Same thing works with negative exponents. So the negative 2 comes down in front, and if I subtract 1, I'm at negative 3. And if we look at letter D here, letter D looks a little bit messy, but if you remember something from grade 11 math where we learned about exponents, we know we can rewrite this function as x to the negative 6. A positive exponent on the bottom can become a negative exponent on the top, or vice versa. We often wanted to write things as positive exponents, but here it makes more sense to go backwards, to write as a negative exponent. Then my derivative, or in other words, f prime at x, I'm using f prime notation because it was fx, would be negative 6, x to the negative 7. And that's our basic idea for a polynomial function. We can extend that, however, some other standard derivative patterns. Whenever you have a constant, okay, so for example, f at x equals 3, the derivative of a constant is always 0, automatically. And the reason why is, when you have a constant, like 3, it already means 3 times x to the 0. So when I bring that 0 down in front, it's like having 0 times something. Well, 0 times anything always comes out to 0. Okay. However, if you have a constant in front of a function, so for example, 3x squared, a number, a constant 3, your derivative is your constant times that derivative. So in this case, what we can do is we can do 2 times 3, which makes 6, and then subtract 1 from the exponent. Okay, we try the next one. 4 times negative 2 is negative 8, and x to the 3. Okay, so a constant out front with letters, that has a derivative, but just a constant, a number by itself, the derivative is 0. And the last idea is if you have functions that are made up of parts and pieces, you can take your derivative in parts and pieces. So if I look at this last little example here, f prime x, the derivative of x cubed would be 3x squared. And the derivative over here, minus x squared, would be minus 2x to the 1. I just did them as 2 separate pieces. Okay, so I have a few for you to try here. We'll play with these examples. Find the derivatives. Okay, so my derivative is made up of parts and pieces, so I'm going to do each part separately. Derivative of that piece, 5x4. Derivative of this piece, I'm going to do 2 times 3, which makes 6, and x to the 1. And the derivative of this piece, well, the derivative of 2 is 0. Okay, there's no x's involved, automatically goes to a 0. And we don't usually write that 0 in there, so my preference would be just to write this. Okay, you try the next one. Pause it and give it a try. So f prime x would be negative 1x to the negative 2 plus 8x to the 1. Okay, don't forget to multiply the constant by the exponent. Okay, try the next one. This next one's got something weird going on in it. It's got an x cubed on the bottom. We don't like those. What we want to do is rewrite this equation and bring this up to the top. And I can do that by making the exponent a negative. Okay, the number didn't change. The 4 is still a 4, but the exponent became a negative. Okay, everything else also stayed the same, but this is a better form for us for taking derivatives. I can do each part separately now. So negative 3 times 4 is negative 12, x to the negative 4, minus 8x to the 1. Don't forget this exponent has a 1 on it, so minus 2. And no x is left. Now I erased it, but I was starting to write x to the 0, but x to the 0 doesn't have any meaning, so that's why I erased it. Okay? And then the last one. Now, the last one's a little tricky. It looks like it's got a whole bunch of parts and pieces. So when you come across something that's got a bunch of parts and pieces, in particular, x is on the bottom, we need to rewrite this equation. We're going to rewrite it with a common denominator. We'll split this into two pieces. And then we're going to simplify each piece. By simplifying, I mean I can cancel an x from the top and the bottom over here. So I end up with 2 over x minus 3 over x squared. And I don't like having x's on the bottom, so I'm going to bring those back to the top. So I have an equation for y that involves parts and pieces, yes, but no x's on the bottoms and no fractions with x's on the bottoms in particular. Now I can take my derivative. So my derivative is negative 2, x to negative 2. Let's multiply these, be careful with signs, plus 6, x to negative 3. And at the end, if you wanted to, you could rewrite this back to the fraction form. That might make it easier to work with down the road, but I'd be totally fine if we just left it in the exponential form. Okay, that's our derivative. That's a really big idea. Some questions I need you to practice. Number one's got a whole bunch of letters to it, but I need you to be really good at derivatives because the rest is calculus is based on this derivative. It's an algebraic model that represents our instantaneous rate of change at any point.